Chapter 7, Automatic Fire Sprinkler Systems. Our objectives for this chapter: describe an automatic fire sprinkler system, discuss the myths and realities associated with automatic fire sprinkler system operation, list and describe the different components that make up an automatic fire sprinkler system. List and describe the different types of automatic fire sprinkler systems. Describe the different types of automatic fire sprinkler systems and the best application for those systems. State the factors that determine requirements to install an automatic fire sprinkler system. Discuss the design concepts behind an automatic fire sprinkler system. List and describe different occupancies and commodity classifications. Discuss the inspection and testing requirements for automatic fire sprinkler systems. Automatic fire sprinkler systems. These systems are networks of underground and overhead piping fed by an automatic water supply. Upon activation, sprinkler heads connected to the piping at specific intervals apply water over a fire area. They have been used for over 125 years to protect property and provide life safety. They are unmatched in accomplishing the primary goal of controlling a fire. Dispelling disparaging myths about these systems require further education for the public about how they work. They are ready to operate without human interaction and thus are practical to use. Automatic sprinkler systems offer reliable, effective, economical, and proven protection for buildings and homeowners, including protection of valuables, properties, and lives of their family, members, employees, and other occupants of the building. Effectiveness is property protection. The basis for fire sprinkler system design is to keep a fire at relatively small size and under control, not necessary to extinguish it. So, for example, a fire starts in a bathroom after a social event. The fire grows quickly, and as heat rises, the sprinkler head nearest the fire activates. However, the growth of the fire is rapid, and a second head activates. At this point, approximately 5 minutes from the start of the fire, the room falls below the remaining sprinkler head's activation temperature, so no other heads activate. With another 5 minutes, the fire department arrives to find the fire is out. The emergency responders turn off the sprinkler system and replace the activated sprinkler heads before turning the system back on. Having a fire sprinkler system can improve the chance of a positive outcome, not only for the business, but all parties in the community that would be affected by a large fire. Effectiveness and life safety. The purpose of a commercial or industrial fire sprinkler system is not necessarily to provide life safety, but to provide property protection. However, NFPA statistics show that when a wet pipe system is installed, there's an 86% reduction in fire deaths compared to buildings that do not have a sprinkler system installed at all. This information indicates that sprinkler systems provide some level of fire safety just by activating and applying water to the fire. Many of these sprinkler systems not only apply water to protect property, but also interact with other building systems to further life safety goals, such as fire alarm and detection systems, on and off-site monitoring systems, elevator, smoke control, and access control systems as well. All these help to manage the fire danger and improve building occupant chance of avoiding injury or death. A sprinkler system is made up of many different components, most of which require list or approval from a second third-party testing and certification laboratory. So let's look at our first part, pipe and fittings. Pipe and fittings join together to provide a conduit for the water that flows to and then out of the fire sprinkler heads. Common used joining methods are as follows: threads, grooves, flanges, welds, solders, heat fusion, brazing, pressure fittings, and glue. Commonly used piping and tubing material is as follows: ferrous piping, black steel piping, galvanized steel piping, copper tubing, alloy materials, and chlorine polyvinyl chloride, or CPVC, which is the dominant type used in residential installation. And of course, we can't fit the ever-popular brass fittings. There are many different types of fitting connections, piping, valves, sprinkler heads, and other components, including such things as seen here in our picture: elbows, T's, flanges, crosses, unions, couplings, bushings, plugs, and reducers. Your commonly used fitting material can be cast iron, malleable iron, rough steel, forged steel, or rough copper, and of course CPVC. Gauges. Pressure gauges are small but important component of a fire sprinkler system. Some systems have only water gauges, but others have air gauges, depending on whether or not it's a wet pipe or dry pipe system. Water gauges are typically installed on the supply and system side of valves and pumps. Air gauges are installed on the system side of certain valve systems, air sources, air supply lines, and quick opening devices. Gauges help firefighters and sprinkler system contractors and building maintenance workers to determine the available water or air pressure at the gauge location. It can also be used to detect a problem when the reading is outside the normal expected values. Gauges should not be subjected to freezing temperatures and should have a control valve capable of draining them. Valves. Each of the different types of sprinkler systems use a particular valve design specifically for the system application. Without valves, there would be no way to control the water supply or flow in a sprinkler system. Looking at our water control valves. When open, water control valves permit water to flow into and through the system. When closed, they prevent water flow or isolate parts of the system for service. One or more valves may be necessary depending on the size of the building. They should be installed in locations that are clearly accessible or marked for emergency personnel to have readily access to the valve. All water control valves must be of the indicating type. These valves should have a permanent metal or rigid plastic weatherproof sign identifying the area the valve services. All must be able to handle 175 psi or carry an appropriate rating for an anticipated pressure above 175 psi. Check valves. These permit water or air to flow in only one direction. They prevent water or air from flowing back in the direction of the supply. Drain valves. They provide a way to remove all water from the fire sprinkler system. When open, the main drain valve provides a way to flow water and monitor the system's static and residual water pressures. The inspectors test the valves. An alarm test valve provides a way to simulate sprinkler system water flow to verify that alarms are properly operating. You have an isolation valve, which provides a way to segregate components or sections of the sprinkler system when service or maintenance is necessary. A pressure reducing and pressure relief valve manage the system's water pressure. Then you have a general purpose valve, and those are usually a global type or quarter turn valve found on the smaller air and water trim lines. They isolate components or allow air or water to enter the main fire sprinkler system valves. Pipe support and stabilization assemblies. The majority of sprinkler piping runs horizontal across a building ceiling. Piping is held in place by the following. Such things as bracing, guides, and restraints hold the pipe in position and prevent movement. Hanger assemblies consist of fasteners or glands, thread rods, and rings that hold the pipe in place. Fasteners secure other components to the structure and must be of the appropriate type. With exception of material that passes fire tests and have listed purposes, all hanger and supporting components must be made of some sort of ferrous material, which can handle the heat of fire better than aluminum or copper. Hanger assemblies must be able to hold 5 times the weight of the water-filled pipe plus 250 pounds. Spacing and location of the hanger components depend on the size and type of piping. NFPA 13 standard for the installation sprinkler system provides the maximum allowed spacing required for various types of piping material. Automatic sprinkler heads. An automatic sprinkler head is a spray device that distributes water over a limited area at a designated flow rate. With few exceptions, sprinkler heads are heat activated and operate at predetermined temperatures. Because each head operates independently, only the heads that reach the critical activation temperature will operate. Sprinkler heads should have a listing or approval obtained by the manufacturer through recognized testing agencies such as UL or FM Global. Fire sprinkler head components. First, you have the frame, which is a central component that holds the other pieces of the sprinkler head in place. You also have a heat-sensitive element, which can be seen here in your picture on the right. They release when the critical activation temperature is reached. The 3 common types are metal, gas, and some sort of solder type material. They have a higher temperature rating for buildings with higher ambient ceiling temperatures. You have an orifice, which is the smooth opening in the head through which the water flows from the pipe. The size of the orifice regulates the amount of water flow. It may be as small as a 1/4 inch and as large as an inch, depending on the water supply and, of course, the available water pressure. You have an orifice cap, which forms a tight seal that keeps the water from flowing until needed. You have a deflector, which can be seen here, and that breaks the water stream into smaller droplets and forms a relatively even distribution spray pattern. They can be trim, ring, cover, cup, or exclusion plated. They appear to be only decorative, but may be required as part of the listed ensemble to meet fire resistance rating for the ceiling or wall. Sprinkler head wrench is a tool designed to install or remove a sprinkler head. So looking at our types of sprinkler heads, you have an old style head, also known as a conventional head, and were the majority of the heads until the 1950s. It could be oriented to discharge water up and down with 40 to 60% of the water initially flowing downward upon activation. Still being produced today, but NFPA 13 limits the use to 4 storage vaults in situations that require unique water distribution patterns. Your standard spray heads emerged in the 1950s and remain the most prominently installed today. They can point in only one direction, and they have several different categories. First, you have the pendant, which points down. You have the upright that points up, and you have the sidewall, which is installed parallel to the ceiling or the floor. The head orientation is critical to the successful installation of a sprinkler system. Placing a head incorrectly will compromise the ability of the head to perform its intended function. You also have specialty heads, which emerged over the past 35 years to handle unique challenges in design situations. They have different physical characteristics from those standard spray sprinkler heads. They include some of the following subcategories, such as dry sprinkler heads, for environments where the temperature cannot be maintained at 40 degrees Fahrenheit or higher. Corrosion-resistant heads, which are specified for the environment that promotes the corrosion. Institutional sprinkler heads, commonly found in mental health, correctional, and detention facilities. You have open sprinkler heads, used for deluge sprinkler systems and flowing water from all heads over a large area without waiting for heat to activate them. You have on-off sprinkler heads, which protect areas where water damage is a great concern, such as computer rooms or museums. You also have quick response sprinkler heads, which use a thinner or less massive material for the heat-sensitive element. You have extended coverage sprinkler heads, which discharge water over a greater area than the standard sprinkler head. Early suppression fast response sprinkler heads, known as ESFR. They discharge great amount of water to penetrate strong updrafts and are designed to spread a fire, are designed to suppress a fire, not just control it. You also have large droplet sprinkler heads, which may be seen in facilities, but few manufacturing still produce heads, and MPA 13 no longer discusses them. Control mode specific application sprinkler heads are designed to control high challenge hazards, such as in-rack or intermediate level sprinkler heads, which provide protection within your store tracks. You have vertical sidewall sprinkler heads, which distribute water like a sidewall head, but the head installation is in a pendant or upright position. You also have attic sprinkler heads, which are installed over the peak of the attic. We have concealed combustible space sprinkler heads that protect areas such as interstitial space construction with combustible material. You have residential sprinkler heads that must operate subsequently quicker than your standard fire sprinkler heads. You have concealed heads, flush sprinkler heads, ornament sprinkler heads as well. Identification, labeling, and markings on sprinkler heads. Your sprinkler identification number, which was mandated in 2001 by NFPA, requires manufacturers to assign a unique character and number to identify each head, which distinguish operational characteristics from head to head. It eliminates the use of traditional terms and identifiers discussed in previous sections, including the manufacturer, the temperature rating, the type of head and model number, the K factor, the SIN number, and list of approval agencies. The K factor establishes a mathematical relationship between the pressure and the flow from a sprinkler head, with Q being the discharge in gallons per minute, K being the discharge coefficient for the orifice or the sprinkler head, and P being the water pressure in pounds per square inch. The relationship determining the flow is expressed with the formula Q equals K times the square root of P. Types of systems. These systems are the most commonly installed types of systems and are the basis for other types of water-based fire suppression systems. First being is your wet pipe system. And these are the least expensive, most frequently installed. They are the easiest to maintain and the easiest to modify, and the most reliable type of fire sprinkler system available. They are preferred to other types because water in the pipe because water is in the pipe at all times. So the water flow is immediate after the sprinkler head is activated. It should only be installed in environments that are not prone to freezing. They require a dedicated and automatic water supply. They are common in almost every type of building and usually have some of the following type components: an alarm check valve or other flow detection alarm device, which are used to provide an alarm and function to notify the water is flowing, and to act as a check valve to hold pressure in the system and not allow the fire sprinkler water to flow back into the potable water supply. They may be mechanical with a water motor, gong, or electrical with a retard chamber and pressure switch tied to an electric bell, fire alarm, or monitoring panels. They limited area sprinkler systems, installed only to protect a large storage area or basement of building, while the building itself does not require full system installation and does not require a separate and dedicated water supply. It is supplied water from domestic water supply only. Alright, as seen here, here's your typical wet pipe system with the risers, check valves, and the various heads and switches. Dry pipe systems protect an area of the building where the temperature falls below 40 degrees Fahrenheit. They can be used for unheated warehouses and attics, loading docks, parking garage, and commercial freezers. Instead of water, they are pressurized with air or nitrous gas until the system is activated and floods the pipe with water. Systems must be installed where the incoming water supply, dry pipe valve, air compressor, and associated components stay in a heated and protected area to prevent the water from freezing. The dry pipe valve is the key component preventing water from entering the dry pipe system. They may be dry pipe valves operated on an air to water flow differential or ratio with design principles. For example, the air to water differential may be 1 to 5, where 1 pound of air pressure will hold back 5 pounds of water pressure. When one or more sprinkler head activates to reduce the air pressure, the air to water ratio is disrupted, thus allowing the water to come and fill the dry pipe valve, causing the clapper valve to swing open and begin to flood the system. Systems may have accelerators or exhausters installed. An accelerator attaches to a dry pipe valve and senses system air pressure loss. When the pressure loss occurs, the accelerator opens an internal exhaust valve to redirect the pressure air to distribute the difference and force the clapper valve to open and latch. And this can either be mechanical or electronic. It's just a way to speed up the process. Exhausters can be attached to the dry pipe valve or any location where there is a 2-inch piping. They sense rapid loss of air pressure, open a port that purges the air out of the system at a rate roughly equivalent to 15 open sprinkler heads. The process allows the clapper valve to open more rapidly and remove air to accelerate the speed at which water fills the pipes. Systems are more complex in general than wet pipe systems as a whole, and they can include the same or similar different parts. Here's a great picture of your dry pipe system. Notice the various components. Our next system is a pre-action system, which uses closed sprinkler heads like a dry pipe system, and under normal conditions there is no water in the system piping. They may have a low pressure as well as supervisory air in the piping. Unlike dry pipe systems, release of the pre-action valve is usually caused by a fire detector or an activation switch. Most require 2 separate events before the water is discharged. A fire detector must activate the pre-action valve so the water flows into the piping, essentially making the system a wet pipe sprinkler system. A sprinkler head must also activate to flow the water. The pre-action valve can be released by various activation methods. It can be either hydraulic, pneumatic, or electrical. Hydraulic uses a quick response sprinkler head on a wet pilot line to release the pre-action valve. The pneumatic uses a quick response sprinkler head on a dry pilot line, which releases the pre-action valve. And the electrical uses heat, smoke, or flame detectors to interface with a fire control panel to release the valve. Operational arrangement provides progressive higher levels of certainty that there is a fire before the water flows, such as a non-interlocking, which follows the requirements for two separate events to occur. You have a single interlock, which follows the requirements that a detector releases water into the pipe. You have a double, which requires that both the detector and sprinkler head activate before any water flows. Other operational features include activation of detectors in different zones before the valve releases the water. Basically, this is known as a cross-zone detection. The use of low air pressure to monitor a pipe's integrity. The use of high air pressure to hold the pre-action valve closed, and pre-alarms, trouble alarms, and supervisory alarms to indicate a change in the system status, as well as a manual release capabilities. Again, here's another picture of a pre-actionary system. Next, we have a deluge system, which operates in a manner similar to your pre-actionary system. Both require a fire detector activation or a manual station release to open the system valve so water will flow into the piping. However, the major difference is that these systems have open sprinkler heads without heat sensing release before water is discharged. Once water reaches the open head, the discharge is immediate and simultaneous from all the sprinkler heads in the system. This arrangement provides large amounts of water over predetermined areas. Operationally, the deluge valve receives the appropriate signal from the detection system to release the clapper. And again, you have the electric, hydraulic, or pneumatic methods to operate. These systems usually protect high hazard occupancies, such as power plants, aircraft hangars, woodworking facilities, explosive and ordnance factories, refineries, cooling towers, and chemical storage and processing facilities, to name a few. Residential sprinkler systems. In order to protect property and life safety, these systems are designed to do the following: prevent flashovers in the room where the fire starts, improve the occupant's chance for rescue or escape. Manufacturers have gained approval to make dry pipe valves, but the vast majority are still wet pipe systems in residential homes. The main observable difference compared to commercial sprinklers are the pipe fitting, hangers, fasteners, valves, and residential systems tend to be smaller in diameter and size. Instead of steel, the primary material is CPVC, copper, polyethylene, or polybutylene in earlier systems. Many are supplied water by an appropriate sized domestic water line fed from a reliable community water system. Some have a specifically dedicated water line. Others are supplied by store water sources with an automatic operating pump. Residential sprinkler heads must meet different testing criteria than a standard fire sprinkler head. They must prevent the amount of harmful fire and byproducts associated with temperatures from reaching levels that could inhibit rescuers or safely exiting by the occupants. Residential systems do not require sprinkler heads to be installed in certain areas, such as bathrooms that are less than 55 square feet, closets and pantries no greater than 24 square feet and no more than 3 feet deep, garages, Open attic porches, carports, attics, equipment rooms, and concealed spaces are also immune from having sprinkler heads. Model codes by NFPA and ICC establish requirements for your automatic sprinkler systems. They are primarily based on the use and occupancy conditions. Thresholds specific to use occupancy conditions actually establish whether the code requires or omits an automatic fire sprinkler system, such as occupant load, building height, storage conditions, and the number of levels above or below exit discharge. Thresholds can influence the design of a building if the following conditions apply: limited space, a tight budget, or a developer does not want to install fire protection that is not required by the model code. Published for sprinkler system design and installation standards are available from Model Code and Insurance Organization. NFPA 13, 13D, and 13R seem to factor into more installations than any other available standard. NFPA 13 standard for the installation of a sprinkler system. The performance objective for the first edition, created in 1896 of the standard, to the most current edition is to maintain control of fire to the point that emergency responders can complete the suppression activities. Controlling the fire necessities and containing the fire to a general area of origin. Sprinkler heads should cover all spaces in a building, including concealed, combustible spaces, attics, and in some instances, the spaces above or below the ceiling. The same requirements and performance objectives apply to all occupancies, committee, and storage conditions covered by the standard. Every system design establishes a minimum performance level for the occupancy based and evaluation of the hazard. Although controlling of the fire remains the basis for NFPA 13, in many instances the sprinkler system is more than adequate to extinguish the fire before manual firefighting is necessary, which remains one of the most widely used NFPA standards. NFPA 13D is the standard for the installation of sprinkler systems in 1 and 2 family dwellings and manufactured homes. First published in 1975, it addresses the residential fire protection problem by placing sprinklers in the area of the home where a fire would most likely start, including such places as your kitchen, living room, and bedroom. Sprinkler head installation was excluded from, of course, small bathrooms, closet, and underneath areas such as attics. The standard established that the system must be economically viable, provide sufficient time for escape or rescue, and prevent flashover. Subsequent revisions of the standards on data to develop requirements for sprinkler head design, specifically for residential application. NFPA 13R, standard for installation of sprinkler system in low-rise residential occupancies. This standard addresses residential fire problems with occupancy such as hotels, motels, apartments, condominiums, and in some cases large single-family dwellings that reach 4 stories. It loosely follows NFPA 13 requirements, including the installation of at least one fire department connection in buildings over 2,000 square feet or more than 1 story. Sufficient water to support multiple sprinkler heads flowing simultaneously, as well as design provided by hydraulic calculation. The hydrostatic testing consistent with the NFPA 13 requirements is also in there. It follows NFPA 13D concepts on placing of sprinkler heads in areas where fires are most likely to start. The standard has evolved to deal with the technological advantages to other classifications to existing requirements. Other fire sprinkler system standards. Other standards dealing with fire sprinkler systems are typically used in one of the following situations: when there is a level or hazard exceeding the scope of NFPA 13, when the standard has specifically designed requirements for the hazard, or when the approved authority requires the use of a different standard. These standards include such things as NFPA 30, 30B, 214, and 804. A few insurance providers develop their own standards for use at their clients' facilities. The design professional must determine the best suited system to use. In some instances, more than one standard may apply to a given facility, and the design professional will reference more than one of these standards to determine the best fire protection system to design for the particular hazards in the building. Design professionals. Design professionals classify the occupancy, communities, or storage arrangements that the system must protect relevant to the level of severity of a potential fire as a base for most system designs. They determine the hazard by evaluating the following: combustibility, amount of combustibility, storage arrangement, the rate of heat release of the commodity, and the materials produced. The system design must deliver enough water to absorb the energy from the fire so it does not grow any larger. NFPA 13 established a number of hazard classifications based on occupancy, commodities, storage arrangement, and use of plastics, rubbers, and other rolled paper storage. They decide whether to use a pipe schedule for the design or a hydraulic design the system. Very few pipe schedules are specified, and few authorities accept pipe schedule designs unless they are tied to an existing pipe schedule system. Most design professionals choose to use hydraulic calculations. The system uses density area curve, which provides a graph which represents the minimum amount of water that the system must provide and its most remote point. They consider modifiers and qualifiers as well. A design density only applies to the areas of the building that meets the characteristics of the hazard group being referenced. The square footage of remote areas increased by 30% when the fire sprinkler system is either a dry or a pre-actionary type system. They determine the estimate flow and pressure requirements. They also determine if the available water supply is adequate to support them. The basis for the design of an NFPA 13 system is as follows. The professional must determine these factors before the design can be moved forward: the hazard, the design density required to protect the hazard, the water supply necessary to support the system demand, and when these are determined, the designer will provide the best system to control or extinguish the fire. Automatic sprinkler systems must go through an approved process to be accepted as a system that is ready to operate and perform as designed. Acceptance and inspection testing is performed during and at the conclusion of construction of the system. After inspection and testing is complete, the installer must provide documents to the approved authority. First, you have flushing. Before connecting the water supply to a fire sprinkler system, the incoming fire line requires flushing. Once it is determined that the discharge water is safe, the control valve must be fully open to allow the water to discharge from the pipe and meet one of the following criteria: a rate of 10 feet per second, equal to higher than the system demands, or the maximum flow rate available to the system under fire conditions. Flushing the line should continue until the water flow is clear. Next, you have hydrostatic and air test, which is one of the most important tests performed during the construction phase. It requires pumping water into the sprinkler system to subject pipes, fittings, valves, and other components to a predetermined pressure for a minimum time duration, usually 200 psi for 2 hours. This system is a dry or pre-actionary system, and the air test is also required. This test subjects the system's piping to allow a 40 psi air pressure over a 24-hour period. A maximum loss of 1.5 psi is allowed over that period. 240 psi are considered the high end pressures exposed and therefore are good indicators of the integrity of the system. Hydrostatic test for residential systems. For NFPA 13 sprinklers, the hydrostatic test pressure should be equal to the water pressure of the system source. If the system requires a fire department connection, the test must follow the requirements of NFPA 13. Visual inspection basically confirms that the design and installation meets the minimum standards and are consistent with the approved plans. It determines if the system has any damage or leaks and if the components are of the right size and correct in location, and if the components are the type specified. It is common to perform more than one visual inspection during system installation, congruently with the hydrostatic test, operational test, and final inspections. The operation of components. Any component that is capable of movement, whether it be manual or automatic, requires an operational condition testing. Components that should be tested are as follows: your control valve, your movable fire department connection components, your water flow switches, your tamper switches, your drain valves, your automatic drip valves, gauges, pumps, automatic filling devices for your tanks, quick opening devices, dry pipe, deluge, alarm, and pre-actionary valves as well, and any device that regulates the pressure. For many components, this step only requires the following action. Operate a valve to verify movement of water through the system. Manually moving a component to make sure it has free range of movement, and observing that a device functions as performed and as design required. Finally, you have the main drain test. This is a very simple test. It establishes that incoming water supply is adequate and there are no impairments to the piping and valves. The tester follows these steps. Look at the system water pressure gauge, record the static pressure, fully open the main drain valve and permit water flow to stabilize, and then look at the same gauge, record the residual pressure, and then shut down the valve. Periodic inspection, testing, and maintenance. Testing should be in accordance with the established intervals listed in your NFPA 25 standard. Testing and maintenance of water-based fire protection systems. A simple visual inspection of a system can reveal leaks, corrosions, and damage to critical system components. Water flow tests can determine if the system is still able to provide the required water capacity and pressure, or determine if there is a closed system control valve. A drip test determines if the dry deluge or pre-actionary valve will release and deliver water to the system in the appropriate time. A hydrostatic test on an underground FDC can determine if the piping remains intact or will fail when subjected to the apparatus pump pressure. Where cold weather conditions dictate, daily inspections of dry pipe, pre-actionary deluge systems, enclosures are necessary. Whether it be weekly, monthly, quarterly, or semi-annual, inspections should be performed. Annually, all systems should receive a complete visual inspection and an operational test. Every 3 years, a dry pipe system is required a full test. Every 5 years, a sample of extra high temperature sprinkler heads needs to be tested. A sample or fast or quick response sprinkler head requires testing initially and after 20 years of service, and then every 10 years thereafter. At 50 and 75 years of service, a sample of all sprinkler heads are required testing. Impairments to fire sprinkler systems can result in component failures and lack of proper inspection, testing, and maintenance. Summary. Automatic fire sprinkler systems are not just a series of pipes and sprinkler heads randomly placed throughout buildings. They are engineered systems designed to control a fire within minutes of the fire starting. The basis for commercial and industrial fire sprinkler systems design is not necessary to extinguish the fire, but to keep the fire at a relatively small size and under control until the fire department personnel arrive. Automatic fire sprinkler systems offer building owners and homeowners a reliable, effective, economical, and proven protection system that will keep them from losing the things they value, including their property and the lives of their families, employees, and the occupants of the building they own. For well over 125 years, properly designed, installed, inspected, tested, and maintained automatic fire sprinkler systems have provided property protection and life safety with unmatched success. The model code permits some increase and some reduction in building performance and construction characteristics when a full automatic fire sprinkler system is installed. Though fire sprinkler systems may seem simple, they require an understanding of the hazard, the competent design layout, installation, periodic inspection, testing, and maintenance, and reevaluation to ensure that the hazard has not changed to the point where the original system design and installations are no longer adequate to protect it. The different types of automatic fire sprinkler systems may have similar characteristics, but not all systems are alike, and to assume so is a mistake. Change in occupancy, content, storage, arrangement, and processes can render a sprinkler system inadequate and may require a different type of system to protect the building or structure. Okay, gang, we've covered a lot, so make sure you handle the objectives, do your review exercises. And if you have any questions, you can email me at aroberts@athenstech.edu or give me a call in the office. Until next time, be safe and have a wonderful day.